Hello, and thank you for joining us. Our presentation on what is energy engineering will be short, no more than 20 minutes, followed by a brief demonstration of Slipstream's energy modeling tool, Sketchbox. We plan to leave ample time for questions at the end, but feel free to post any that come to mind in the chat as we go. We are recording this presentation and the Sketchbox demonstration so that we can make this information available to other students and orgs that were unable to join this live presentation. My name is Jennifer, and I'm joined this evening by my colleagues Emily, Gabby, and Letty. Each of us are energy engineers with Slipstream. Emily and Gabby both got their start with Slipstream through our internship program, so are a great resource if you have any specific questions regarding that opportunity. We plan to cover why we care about sustainable buildings, energy efficiency of building systems, some discussion on what energy engineers do, and lastly, a high-level explanation of energy modeling followed by a demonstration of Sketchbox. Let's begin by discussing why we care about sustainable buildings in the context of climate change. As you likely have heard, the climate is warming. This graph, courtesy of NASA, shows the change in global surface temperature from 1880 through 2020. Compared to long-term averages, 19 of the hottest years have occurred since 2000. As the climate continues to change and we see an increased frequency of severe weather events, we need to adapt, including our approach to building design. Energy performance, an important aspect of resiliency, must be considered in both new building design and retrofits of existing buildings. Buildings account for approximately 40% of the United States annual energy consumption, or 400 billion in energy cost. There is substantial opportunity to reduce these values. This chart provides a breakdown of energy consumption by sector. As you see, when we combine the residential and commercial building sectors, we arrive at 39%. It is also important to note that commercial building energy usage is the fastest growing sector, and that trend is expected to continue. Coincidentally, the building sector also represents about 40% of US carbon emissions. Now let's evaluate energy consumption from a cost perspective. On average, energy costs represent 28% of operating expenses for a typical office building. 30% of that energy is consumed unnecessarily due to inefficiencies. That means almost 10% of operating expenses are due to those inefficiencies, and those inefficiencies provide an opportunity for building owners to improve building performance, save on operating costs, and lessen the building's environmental impact. Now let's identify some of that opportunity to reduce wasted energy, beginning on the outside of the building with the building envelope. Letty?
Thank you, Jennifer. So I will be talking about the building envelope, which is part of the building that forms the primary thermal barrier between the interior and the exterior. The envelope plays a large role in the amount of energy a building uses, the comfort of the occupants in the building, and the natural lighting and ventilation in the building. Included in the envelope are the roof, windows, doors, walls, and floors. When these components are properly sealed, the flow of outside air coming into the building is minimized. This is known as the building's infiltration rate. A lower infiltration rate makes a building more energy efficient by reducing heating and cooling loads. So the temperatures set by a home's heater or AC system are less impacted by this outside air. In addition to infiltration, properties such as thermal resistance and window-to-wall ratio come into play. Thermal resistance is expressed in terms of R value or U factor, with U factor and R value being the inverse of each other. Thermal resistance is a measure of how well a component prevents heat from escaping the building in winter months or entering the building in summer months. Generally, the larger the R value or the smaller the U value, the better. Energy codes define minimum values depending on the specific climate zone of a building, with colder climates requiring a higher R value. The U factor for walls is calculated by using the combination of R values of its continuous insulation and its cavity insulation. Continuous insulation will have a much larger impact overall than cavity insulation will have. Window to wall ratio should also be considered since it ties into both infiltration and thermal resistance. An ideal ratio would be generally 40%. As the window to wall ratio increases, so does the potential for more air leakage and thermal conductance. Even the best performing window can't be outperformed by a reasonably constructed wall. Very high window to wall ratios can lead to glare and poor occupant thermal comfort. When evaluating the performance of windows, we want to ensure that we are looking at the assembly U value, which considers the performance of both the glass and the frame. So if you've ever touched a frame in the winter, you know that most of the heat escapes through the frame. So it's important to add frame thermal barriers as well as get glass with good properties. Another property that should be considered is the solar heat gain coefficient, which measures how much heat from the sun is blocked. A solar heat gain coefficient of 1 means that all the heat from the sun passes through the window, while 1 of 0 means that no heat passes through. A lower solar heat gain coefficient is particularly important in hot climates in the summer months. And you can lower this coefficient by installing windows with tinted glass or glazing. So a good building envelope is the foundation to an efficient building. However, you can add to this by taking lighting into account, which Jennifer will talk about next.
Thanks, Letty. So let's start here. The incandescent lamp, which was used in buildings beginning in the early 1900s. We all know the incandescent lamp is an inefficient light source. This shouldn't be surprising as the technology is more than 100 years old. But more importantly, let's talk about why it's inefficient. Looking at the pie chart, you'll notice that we get only 3% visible light for the 100 watts we supply. 90% of that energy is dissipated as waste heat, and 7% is emitted in the non-visible light spectrum. In fact, the word incandesce literally means thermal radiation. This is not a good thing when we are looking to get light rather than heat. In looking at this pie chart, we can immediately see that the fluorescent lamp was a significant improvement. The blue slice of the pie, the visible light, has grown from 3% to 22%, and the losses due to heat dissipation have decreased from 90% to 68%. Just a few short years ago, fluorescent was the predominant lighting technology installed, even in new commercial buildings. In fact, I would venture to guess that most of you may still have at least a few of these in your home. So what about LED? I'll venture another guess that most of you today would opt to purchase this lamp over the fluorescent. LED has truly revolutionized the lighting industry and had significant positive impacts on energy efficiency. Let's look at why. The blue area, or visible light on our chart, is now the predominant output. This LED lamp produces 60% visible light and only 20% heat loss. So what is efficient lighting? It's doing more with less. Each of these lamps we looked at generates the same amount of light or lumens, but we spend 100 watts to generate that light with an incandescent bulb, 27 watts with a fluorescent, and only 16 watts with the LED lamp. Now, choosing an efficient technology is important, but the most efficient fixture is one that is off. When you were growing up, how often did your parents tell you to turn the lights off when you left a room? Fortunately, we have several automatic lighting control solutions to help us with this in commercial buildings. We are even beginning to see sensors integrated into fixtures. So not only can we automatically turn off lights in spaces when they are unoccupied, but the granular sensing array inherent in having a sensor in each fixture allows us to do this with confidence in less time following actual vacancy. Or when a space has access to sufficient natural light, we can dim or turn off electric lighting. Integrated sensors allow fixtures nearest the windows to dim more than those further from the windows. Fixtures can dim more on a sunny day than on a cloudy day. The savings potential when coupled with LED lighting is significant. Moving along, Emily will now discuss energy efficiency as it relates to HVAC.
Thanks, Jennifer. HVAC, often pronounced HVAC, stands for heating, ventilation, and air conditioning. This building system is important for occupant health and comfort. Low ventilation in a building can result in dust and dirt accumulation, health issues, drowsiness, and noticeable odors. Heating and cooling keep occupants at a comfortable temperature by adding heat to make up for the heat loss to the building envelope in the winter or by removing heat due to heat gain in the summer or other internal loads such as computers, lighting, or even the people themselves. There are many different system types that vary by size, fuel type, and configuration, and different systems are best suited for different building applications. There are various efficiency improvements that increase the efficiency of the equipment itself. However, as with lighting, the most efficient equipment is the equipment that is off. So, first I'm going to discuss a method often used to control HVAC systems. As discussed, ventilation is very important for the health and comfort of building occupants. So, buildings are designed to meet specific ventilation rates. In this example, that ventilation rate is 10 CFM per person with an expected 16 people per floor. In a building with no demand control ventilation, you would see 160 CFM delivered to each floor. However, as seen here, a typical building is not always at its design occupancy. Some floors might have 16 people, but others will have less. Demand control ventilation reduces the outdoor air amounts based on the current or actual occupancy. When the outdoor air is reduced, there's less air and heat to heat or cool, reducing the energy consumption. In this example, demand control ventilation reduced outdoor air supplied by 57% while still providing the ventilation needed for all occupants. The next energy efficiency technology often used in large central HVAC units is energy recovery ventilation, or ERV. Large central HVAC units, like the ones seen here, are called makeup air units. They are the equipment typically seen on the top of large commercial buildings and are used to draw in and condition the fresh outdoor air used to ventilate the building. This system oversees dehumidifying, humidifying, heating, and cooling of the outdoor air to make it more comfortable for the occupant. Now, at the same time, the system is also exhausting already conditioned air that will be replaced by the fresh outdoor air. This exhausted air, when it first enters the makeup air unit, is called return air. As you can see in this diagram, the return air is coming to the makeup air unit at 70 degrees, and the outdoor air is at 30 degrees. Instead of just exhausting the return air, we first put it through an ERV, in this case, an enthalpy wheel. The enthalpy wheel then transfers the heat from the return air to the outdoor air. You can see here the outdoor air after the ERV gets to 60 degrees. This preconditioned outdoor air decreases the amount of heat needed later to prepare the air to enter the building. The same principle can also be applied to the humidity ratio, noted as HR here. The outdoor air is very dry, and the enthalpy wheel transfers some of that moisture from the return air to humidify the outdoor air and make it more comfortable for the occupants. ERVs are also used in the warmer seasons to pre-cool and dehumidify rather than heat and humidify as seen in this example. Now that you have some background on energy efficiency options, we can talk about how energy engineers use these different technologies discussed. Energy engineers can apply this knowledge in many ways, such as researching new technologies or educating the public on energy efficiency measures. At Slipstream, we also apply this knowledge to implement energy efficiency programs, which will be the focus of our energy engineering intern in 2023. So what is program implementation? Using our knowledge of buildings, how building systems interact, and energy efficiency improvements available, each of us works to support a utility-funded custom energy efficiency program. The goal of the program is to improve the efficiency of new construction and major renovation projects. We ideally engage with the building design teams early in design process to gather information on a building and to consult on the energy efficiency options. The results of our analysis are most impactful if provided while the project's design is still in progress. Here's an example of an energy report we may put together for a design team. As you see on the right side, we show the energy cost savings associated with energy efficiency improvements. You will see that some of the improved energy efficiency measures we discussed earlier, such as window assembly U-value or lighting controls, are on this report. The design team is also provided with a monetary incentive for implementing these energy efficiency improvements. On a typical day, we might do multiple different tasks for multiple different projects. We could review building drawings and designs, suggest and encourage energy efficiency options, discuss options with design teams, or investigate energy efficiency measures that the teams request. We also spend a lot of our time calculating the incentives and energy savings for a project. As an energy engineering intern, you will work closely with our team of engineers to help with these tasks. We will start with small tasks such as learning how to read drawings or doing simple calculations, then build up to having discussions with the design teams and doing the total building calculations yourself. So the next logical question is, how do we calculate energy savings for a project? The answer is energy modeling, which Gabby will explain in more detail next.
Thanks, Emily. So, like Emily said, one of the main ways we predict energy savings is through building energy models. So, energy models are useful because they capture the full picture of the energy going in, going out, and being consumed by the building. Generally, the energy demanded by the building is what we call the energy or the building's energy load. So building loads are impacted by energy going in and out of the building. It can be in the form of radiation from the sun, conduction or heat transfer through the envelope, airflow, internal loads. Generally, internal loads add heat to the space. For example, people occupy the building, lights are on in the building, also devices that plug in to the wall, such as computers and copiers. So energy models predict these building loads by simulating the building throughout an entire year using weather data for the building's location and typical occupancy patterns. To satisfy the building load, the building must consume energy. For instance, to meet thermal comfort requirements, HVAC equipment consumes energy to heat and cool the space and to supply fresh air to occupants. To satisfy other requirements, internal equipment like lighting, computers, appliances, etc., also consume energy. Energy models calculate the total energy consumption throughout the year by simulating the energy consumed by all these building components in order to meet the building's load. So if you are hands-on in terms of your learning style, trying out energy modeling can be really fun. Slipstream developed our own energy modeling tool, which we call Sketchbox. While most energy modeling software takes a long time to learn, Sketchbox is quick and easy to use, and it can be used directly on your browser, so you don't need to download anything. We're able to give students free access to the tool, so you should just be able to sign up using your email following the direction on our website. Now I will give a quick demo of the tool. All right, so once you get to Slipstream's website, we have a whole website, our whole web page for Sketchbox. So there's lots of information that you can find on here related to the tool. We have some video tutorials that are out. And when you're ready to start using Sketchbox, you can hit any of these buttons that will prompt you to log in. If you already have a login, you would log in this way. Otherwise, you would go through and create an account. So when you enter Sketchbox, you are first on this project tab. And as the name suggests, you can enter in some basic project information. You can edit the name and location of your project. Another aspect of Sketchbox is comparing your building to energy code minimums. So that is what this dropdown relates to. And if you were to do our internship, a large part of what you would learn about is what energy codes are. So we won't go into detail about that right now. The next tab is where the fun part really begins. So here you can see this is what our building model looks like. Generally, all of our models just look like big rectangles, but it can be helpful to see what the orientation of the building looks like. And as you build more complex models, the geometry gets more complex as well. On the Design tab, you can change the assumed building type. So there are a lot of default settings that will go into place once you change your building type. So if I were to have a medium-sized office, for example, this is the size it's going to assume, the shape it's going to assume. Whereas if I have a warehouse, it's going to assume something much flatter and larger. So that's just one example. And as you navigate throughout Sketchbox, it's fairly easy to figure out on your own through experimentation, but just a few pointers. Any text that is in blue is going to be a Sketchbox default. So you can see here the area is written in blue, which means it is a default value. And if I go in and change it, which I can do, a little refresh button will come up, and that way I'm able to um, go back to the default for that cell. Another thing that can be helpful is if you hover and hold over any box, um, there will be an additional description that will come up that might be helpful for you when figuring out things about your model. So I won't be going into detail about every single input on the Design tab because there are lots, but generally this is the tab where you enter things like geometry. You'll enter in the HVAC system as well on this tab, which will determine if the building is being heated by natural gas or by electricity. You can add shells, which is basically like adding another building component by checking that plus sign up there at the top. You can also um, change how these shells are in terms of adjacency. So for example, I can attach the second office shell to the other office shell, or I can put it on top of the other office shell, just as an example. You can remove shells by going to the bottom of the Design tab and hitting Remove. You'll also see that there is automatically a Site tab, or a Site shell, I should call it, on the Design tab, and this will essentially impact the exterior lighting since that's not really tied to any one shell. The next tab that Sketchbox has is the Schedules tab, and this will impact the occupancy as well as the different equipment use patterns that your model will assume. So, like all other aspects of Sketchbox, you don't need to know this for your building. You can use assumed values. So, if you remember, this is an office that we're modeling here. And so by default, it's going to make some assumptions about typical office occupancy. So there's many graphs here which can be helpful to see what your model is doing. So you can see this is for a typical weekday. It's assuming that for my occupancy, so in terms of people in the building, that is hitting a peak around 8 a.m. and it is starting to decline around 6 p.m. with very limited occupancy from midnight to 6 a.m. You can also see that there's a selection for weekends. So for this example, there's way less occupancy on weekends. And this tab doesn't only impact occupancy, like I mentioned, it also impacts things like the heating and cooling set points. the lighting that's assumed to be on, the domestic hot water loads, and things like that. There are many ways that you can change these schedules, but again, I won't dive into that right now. But you can feel free to play around with that if you'd like. The next tab is our baseline tab, and this is going to impact generally the performance of the baseline building. So when we do energy models, we typically have a baseline model, which is what we're using to compare the energy efficient versions of the building to. So this is going to impact that initial baseline run of the model that we have. You can see here that almost all of these inputs have default values, and these are going to be impacted by things you enter on the design and the project tab. So typically when we build an energy model, we will leave most of these baselines at whatever energy code requires. And then later on in the next tab, we will go ahead and make improvements to those items from code. There's also a baseline tab for the site shell. Like I said before, this impacts exterior lighting. So the last tab, or the second to last tab, is the measures tab. And this is really where we as energy engineers will enter our energy saving measures. So an easy way for us to do this, and what I will show you today, is by adding a measure set. And Sketchbox has a standard measure set built in, which has what we call like our best practice energy saving measures already implemented. And you can see that just filled in a bunch of different energy saving measures. So for example, the first one is to upgrade the roof insulation. You can have the option to not change the roof insulation, and that will keep the value at the baseline value, or you can improve it to a better or a best option. You can also add a custom option for any of these measures. So it's pretty easy to switch between all of the values once you have the measure added. And to add any other measure, you would just add in a measure with this plus sign, enter the name, and then there are a lot of different options for what you can edit in your model. So once you have your measures in, the next step would be to run the model. And it's very quick. Sometimes you might need to try a few times to get the model to run, but it should be pretty quick. And then you're going to have all of these nice results graphs. So we have a table with a summary of the annual savings, and pretty much all of the information you're going to see on this results tab is for a whole year, because that is how our energy models run. And yeah, you can kind of explore these different graphs. One thing that we are usually very interested in is the relative energy or cost savings. So you can see this bottom graph here is really helpful to kind of compare all the different measures that were on the previous tab. So you can see here that the energy efficient lighting is a really big energy saver. This is in terms of cost, but it'll also be a big energy saver in terms of actual electricity consumption. Whereas something like the roof insulation is not as big of an energy saver. So that can be helpful to use this graph to compare and contrast the different measures that you have. Another aspect of Sketchbox that is helpful is you can save and come back to your work. So for example, I can save this project by hitting that save button up there and hitting save project. Once I want to come back to that project, I can then go to that same right corner, hit the folder icon, and open a project. So feel free to play around with this tool. We do have a support button that you can hit, and I think that will get you the contact information um, for support. So you would hit contact support. Also, feel free to get in touch with any of us if you um, are having issues with actually creating an account. Just reach out and we can help you with that. If you hit this documentation button at the bottom, you'll also see that there's a lot of information that you can read about, which will hopefully help you get started with Sketchbox. And that will be it for our quick demo of this modeling tool. I will now hand it back over to Jennifer.
And at this point in time, I just want to thank each of you for attending. And we are here and plan to stick around for a few minutes yet this evening if there are any questions. If questions come to mind later, we've provided our contact information. Please don't hesitate to reach out after the fact. We'd be happy to answer those questions and engage with you about any questions you might have about Slipstream, Sketchbox, and or the specific internship opportunity. Again, thank you for attending.